see our homework?
I want to do with that. So, first of all, polynomials have graphs that are smooth curves, okay? Smooth, continuous curves. If it's a polynomial function, there won't be any sharp corners, no points, no holes in the graph, no asymptotes, nothing like that. It's just a smooth, continuous curve. We're going to be looking at what we call end behavior. Which, believe it or not, is what the graph is doing on either end. Right? Some people call it far right or far left behavior. Alright, so that's attack. The easiest way to determine it is to determine if it's even degreed or odd degree. Okay? Not an even or odd function, but an even degree or an odd degree. Now, the degree is determined by that highest exponent. So if it's the highest exponent is like x squared, it's even degree. If the highest exponent is x to the fifth, then it's odd degree. Okay? Whatever the highest exponent is, it's either even or an odd number, and that determines if it's an even degree function or an odd degree function. Pretty easy, right? So you've got even degrees and odd degrees. But you also have lead coefficients. Alright, can anybody show me what an x squared function looks like? Exactly, it looks like this, right? What about a negative x squared? It's flipped, right? Okay, that's in behavior. What you're showing me, this, it goes up here and it goes up here, that's in behavior. And if it's negative, it goes down here and down here, that's in behavior. That's the far left behavior and the far right behavior. So not only do the even and the odd determine what it looks like, you may know what an x cubed looks like. Yeah, I think that. Yeah. And a negative x cubed would be like this. Okay? So not only does change the Alright. So not only do the degrees determine it, but the lead term, the lead coefficient also determines it. So you could have a positive lead coefficient or a negative lead coefficient. Okay? So if it's even and positive, what does it look like? Yes. It looks like a U. Touchdown. Okay? And it looks like this no matter how many degrees it has. If it's even, it looks like this. If it's even and positive. Now, it could have some more lumps in there maybe, but it's going to be, if it's even and positive, both of those ends are going up. Now, we have a fancy way of writing that, and you do need to know this, okay? Yep. As x approaches infinity, f of x also approaches infinity. X is your x value, f of x is your graph. Basically what I'm saying is, the further I get to the right, as I go far, far, far right with x, the graph goes more and more and more up. Well, x doesn't just go to the right, does it? What other way does it go? This is x, right and left. So as x goes to negative infinity, the further I go left on this graph, what happens with the picture here with the graph with f of x? It's still going to infinity. Yeah, this one has matching in behavior. Even functions have matching in behavior. It's either up and up or down and down. If it's negative, lead coefficient, down with the frown. Again, you can have like 1,000 little lumps in there, whatever. But it's still going to be down and down. X goes to the right. And what happens to f of x? It goes to negative infinity because it's going down. X goes to the left. What happens to f of x? Is that positive infinity this way? It's still going to negative infinity. What? This is x. As x gets bigger, as I go, this is basically as x goes to infinity. So as I go to the right with x, what happens with the graph? Well, it goes further and further down. This one says, as I go to the left with infinity, forever, what happens to the graph? Well, it goes further and further down. Yes, yes.
That's the question.
Yes.
Is it the Disney bumps one less than it has its one? And then also, for that, it always have like as x, one of them will be negative, one positive, and on that positive, and then both negative, both positive.
On an even function, okay, on any function, even or odd, you have to have these two, because these two are your left and your right, okay? This one is saying as I go off to the right, this one is saying as I go off to the left. So those are on every single one of them, because you always go check to the right, it's in behavior, it's far left and far right, so you've got to check these two. Now, if it's an even function in behavior matches. So if it's an even function, I can get this taken care of. These two are either going to be towards positive infinity, or they're going to be towards negative infinity. Because it's even, they match, okay? They both match. They're up and up, or they're down and down, okay? Because they match. So it's either going positive infinity, or negative infinity, right? Okay. Odd functions don't match, okay? Odd functions, a linear function is an odd function. Or you could even have one that, it's like a mountaintop climbing. But you're still going to be checking it as x goes off to the right and as x goes off to the left. That part doesn't change because I want to know what's happening far right and far left. That part does not change. So on this one, as x goes off to the right, what's the graph doing that we call f of x? What is that doing? The further I go right, what's happening to the graph? Positive infinity. Alright? And as x goes far left, what's happening to the graph? It's going to negative infinity. Okay? So that's odd for the positive lead coefficient. Let's try odd with a negative. It's just going to look like this. Again, I want to know what's happening at the right. What's happening is x goes off to infinity. What's f of x doing? Negative infinity. And as x goes off to negative infinity. When x goes off to the left, what's f of x doing? So that's your end behavior. That's what's happening on the far left and the far right. Right? Everyone have it now? Some people are still writing. Are you just writing? So write out the end behavior of these. Determine the end behavior that goes. Alright, what's this? As x, as x approaches infinity, what's happening with f of x? It approaches infinity. As x approaches negative infinity, what happens with f of x? What is it? Negative infinity. This is an x cubed. It looks like this. Right, what about this one? First of all, is this even or odd? Even, positive, or negative? Positive. Positive, even. So, as x approaches infinity, what happens with f of x? It approaches infinity. As x approaches negative infinity, what happens with f of x? What about this one? Right, what is, this is a even, negative. So as x is approaching infinity, f of x is approaching negative infinity. As x is approaching negative infinity, f of x is still approaching negative infinity. Right. Okay. Yeah. And you just sort of picture it, because I know if it's a negative positive, it's going to be down. If it's a positive, negative, a negative even, it's going to be down. If it's positive even, it's both up. You just sort of picture it in your head. You do have to memorize what positive and negatives, even and odds, look like. Mm-hmm. Upside down. Right. Mm-hmm. Yep. Any questions about the end behavior? Any other questions? We have one. Alright, we're going to talk about extrema. Alright. When I drew some of these, you notice some of them had these hills and valleys right here. Okay? These are actually turning points. I was going up, and then at this, somewhere about right here, I was no longer going up, and I started going down. Okay? And here I was going down, and then somewhere right through here, I no longer was going down, and I started going up. Okay, so they're turning points. They have special names. They are, well, we have maximums and we have minimums. And from of those two, we have absolutes and relative. Now, the absolute maximum or the absolute minimum is exactly what you would think. It is the absolute highest point on the graph or the absolute lowest point on the graph. That's an absolute maximum or an absolute minimum. A relative maximum or a relative minimum is the highest or the lowest point if you're just looking at a certain section. Okay? So if I was just looking here, that is my relative maximum. If I'm just looking at this section right here, that's a relative maximum. That's the highest point. That is the highest point for that section, right? So that's a relative maximum. So this is a relative maximum, not the absolute maximum. Some people call these local maximums or local minimums, and you'll hear it interchangeably. Looking at this graph, does this graph have an absolute maximum? Right, what does that tell me right here? Goes up to infinity, right. And infinity keeps going forever and ever and ever. So there's not a maximum point. There's not a stopping point. This is okay. This is the biggest one. So graphs can have maximums and minimums, but it doesn't have to have a maximum or a minimum. Think about a line, a linear function. A linear function doesn't have maximums or minimums or local maximums. It's just a line. That's it. Okay, so they don't all have to have it. But how many can they have? Extrema, the maximum number of extrema is the degree minus 1. And then from there, they drop by 2. So let's say you've got a 4th degree polynomial. A 4th degree polynomial could have 3 extrema. 1, 2, 3. 1, 2, 3. So it could have 3. It drops by 2. It can have 2 extrema. Because what does a 4th degree polynomial have to have on the end? What does its end behavior have to do? It has to match. It has to be the same. Okay? Up and up or down and down. It has to be the same if it's a 4th degree. So it's even. Even end behaviors match. So let's just say, for example, just for a second, I really want this 4th degree polynomial to have 2 extrema. I want it to have a hill and a valley. 1, 2. Uh-oh. Can I have that end behavior on a 4th degree polynomial? No, I cannot. So that's why it's out. It can have 3 extrema, or it can have 1. 4th degree polynomial with 1 extrema. And I didn't do both of those negative on purpose. It just sort of happened that way. That was not like it has to be negative. Let's look at an odd. Not too big, because I don't want to have to draw lumps forever. So let's just go to a 5th degree. So 5th degree, we start by subtracting 1 degree. So a 5th degree can have at most 4. Okay, so there's 1, 2, 3, 4. 1, 2, 3, 4. At most you can have 4 extrema. It can't have 3, because if it has 3, what's it going to look like? An even degree. Yeah. So it can't have 3, so we got to drop down to 2. 1, 2. Beautiful. So there's 2 extrema. But it can also have 0. It can have none, even as a 5th degree. There's no hill, there's no valley, there's no change of slope in that at all. That's constantly going up, not as constant, not the same number as others, but it's constantly going up.